Greetings everyone. In this lecture we are going to learn about the seep2d finite element program for seepage analysis. Seep2d is a two-dimensional finite element flow model or seepage model. It was originally written by a guy named Fred Tracy, who worked with the U.S. Army Engineer Waterways Experiment Station. He is long since retired. I knew him early in my career. Great guy. And Waterways Experiment Station is in Vicksburg, Mississippi. It's now called the Engineering Research and Development Center, or ERDC, or ERDIC. And when Fred was worked for the Corps of Engineers, he wrote this this software, and then we built an interface, a graphical interface to seep2d in GMS, the groundwater modeling system, which was developed here at BYU originally under my direction and now is developed and maintained by Aquaveo, a company in Provo, Utah. We are going to be using both GMS and seep2d. The objective of these slides, or this video, is to give a kind of an introduction into how seep2d works. And we're not going to go over the GMS interface. We'll do that through our in-class exercises. But this will give us a little bit of background on seep2d. First of all, seep2d can be used for heterogeneous anisotropic soil properties. Heterogeneous meaning you can have any number of material zones in your model, and anisotropic means kx does not need to equal ky. It can if you want, but can handle any kind of problem. We can do both confined and unconfined flow problems for profile models. A profile model, of course, is when we do a vertical slice or cross section through, say, a dam or a levee or a sheet pile. Confined, we'll talk more about what that means. It basically means the whole problem is saturated. Unconfined means you have a partially saturated region. And so for the unconfined problems, we can actually simulate flow in both the saturated and the unsaturated zone. That's actually what's going on here. This black line, this is a earth dam. This is a problem we're going to be solving later as one of our, I think it's a homework assignment actually. And this black line is the phreatic surface, and so everything above that is in the vadose zone, and everything below that is saturated. So the blue lines here are flow lines. The colored contours are equipotential lines. So we have a flow net. You can see in the foundation we have the equals length to width ratios, and then as the anisotropy varies in the other zones, we have different shapes for those cells. But this is an example of an unsaturated problem. You can also use it for confined flow, for plan view aerial models, or axisymmetric models like flow to a well. But we're not going to cover those this semester. We're just going to do profile models. What it's not suited for, it doesn't do transient or time varying problems. It only will give you a steady state solution, or unconfined plan models, or contaminant transport. But it's great for profile models. Super easy to use. Really great tool. All right, the governing equation used by seep2d is shown here. The right side is 0, so that means we don't simulate internal sources and sinks, nor do we have transient terms, steady state. And since we have kxy and kyx, that means that the principal axes of hydraulic conductivity do not need to correspond to the x and y directions. Or as you can simulate the full hydraulic conductivity tensor. We'll talk more about that later. All right, the modeling process generally has 4 steps. Conceptual, before you build the model, you do model conceptualization, determine your boundary conditions, then you build your finite element mesh, select your analysis options, your material properties. So we'll talk briefly about each of those in these slides. So model conceptualization, you determine your model type. Whether it's plan or profile, again, we're going to do profile problems in this class. Whether you have confined or unconfined conditions, that's pretty easy to determine. What takes a little more thought is determining appropriate boundary conditions. So let's look first at some examples. This is a confined flow problem, the classic sheet pile problem, where water is flowing underneath the sheet pile from the upstream to the downstream direction. In this case, we have 2 constant head boundaries. We would mark this in seep2d as a specified head boundary. There's a simple way to do that. We'd give it this head. You have to determine a datum. And for a problem like this, I would probably just pick the base down here as the datum. And so you'd assign a head value there, and then whatever your elevation is here, you'd assign as a constant head boundary. Everything else is a no-flow boundary. And you do not, when you have a no-flow boundary, you don't need to explicitly select that boundary and assign it as a no-flow boundary, because in these kinds of problems, that is the default boundary condition. So if you do nothing, it's assumed to be a no-flow boundary. Here's another one. Same sheet pile problem. We've seen this before when we're talking about flow nets. We have an upstream clay blanket. In this case, these would be your constant head boundaries, and everything else would be a no-flow boundary. This is the classic Dupuy problem we've talked about. This is actually an unconfined problem. And so in this case, your upstream vertical boundary and your downstream vertical boundary would be constant head boundaries corresponding to the upstream water level and the downstream water level. But now we have an additional boundary when you're dealing with unconfined problems where you have a saturated zone and an unsaturated zone. Somewhere on the back end, you specify what is called an exit face or a seepage boundary, and that is the location where you would expect the phreatic surface to exit. And unlike the Dupuy solution, we do not assume that the exit point coincides with the tailwater. In fact, the exit point exits somewhere along this face, and below where it exits, it's the head is equal to the elevation. So it's a special case of a specified head boundary, and above that, it's just an unsaturated zone. But we just mark that as an exit face. Now, you could mark the entire back side here as an exit face. It doesn't matter how high you go as long as you cover the entire domain where that phreatic surface could exit. Here's another problem. We have we're simulating flow through a levee or a dam. We have an unsaturated zone up here, a saturated zone. This is our phreatic surface. It exits somewhere over here. We don't know where. So these 2 spots would be where you have water covering it, would be constant head boundaries. And then again, up the back from this saturated point all the way up the back here, you mark that as an exit face or a seepage boundary. Now, what do you do if you have sheet piles? How do you treat that? Actually, what you do is when you build your mesh, you just build a crack or a void in the mesh where at the location of that sheet pile. So your mesh would go over, down one side to this point, and then up the other side, and so you'd have a little bit of a gap. Now, how big you make that gap doesn't matter. You can make it really small. It's just as long as is that you have a gap going down. And what that does, and it can join here at a single point if you like, what that does is it makes this a boundary that goes down and up. And remember, the default boundary condition for any boundary is a no-flow boundary. And so that's what this should be. As you go down this side and up the other, that should, and actually in this case all the way over, down and up, that should all be no-flow boundary conditions. And so the point is, for a sheet pile, you just create a crack in your grid. And we're going to do an exercise where we simulate this. It's pretty easy to do. Okay, so once you've decided your boundary conditions, your problem type, you build your mesh. In seep2d, we use triangles and quadrilaterals. Now this says 3-node triangle to 4-node quadrilaterals. I'm going from memory. I think it might support quadratic elements, but I could be wrong. I know for a fact it does support both 3-node triangles and 4-node quads. And any combination thereof. You can use all triangles if you want. You can do all quadrilaterals if you want. It's actually most common to use triangles because you'll, in the GMS interface, automatically generating a grid using triangles is a really fast and easy way to build a mesh. So once you've built your mesh, and by the way, let me back up a little bit. In GMS, the way you build a mesh is you create a polygon representing the boundary of each of your material zones, and then you distribute a set of points along the face, or along the boundaries of each polygon, representing the density of the elements, and then you push a button and it generates all of the interior elements. It's very simple. All right, once you've got your mesh constructed, you select your analysis options. The defaults are plane flow, which is what we do in profile models. Axisymmetric flow is used for flow to a well, which we're not going to do generally. And then this model type is for that only applies for unsaturated problems, which we'll talk about. You also define your units and enter your unit weight of water. And then one of the cool things about seep2d is it will automatically generate flow lines for you. Not GMS will generate the equipotential lines, but it'll generate flow lines, which we can use to visualize the solution, which is really nice. All right, now for unconfined problems, things are a little bit trickier. Flow is modeled in both the saturated and unsaturated zone. seep2d will compute the location of the phreatic surface, which of course is the water table surface, or where the pressure head is equal to 0. Above the phreatic surface, the pore pressure becomes negative, and below the phreatic surface, the pore pressure is positive. What do I mean by negative pore pressure? And why do we even have water above the phreatic surface? Well, if you have, basically you have water that's pulled up into the vadose zone, we call it, in the unsaturated zone through capillary rise. And so in reality, you could have a small zone which is fully saturated but has negative pore pressures due to that capillary rise pulling the water up. And then above that, it's partially saturated, but again, it is negative pore pressures due to the pull of the capillary rise. We just, for simplicity, assume that the entire zone is at least partially saturated, although the saturation level could be really small. But again, seep2d will automatically iterate to determine the correct location of this phreatic surface. And then basically what it does in the unsaturated zone is it calculates a very small hydraulic conductivity. It's some fraction of the saturated hydraulic conductivity. So you get a little bit of flow there, but it's not much. So most of the flow is in the vadose zone. And mostly that technique is just to allow you to iterate and find the correct location of that phreatic surface. And what we're mainly interested in is flow in the saturated zone. So in the unsaturated zone, remember, well, pretty much anywhere in the model, the total head is equal to the pressure head plus the elevation head. And in the unsaturated zone or above the phreatic surface, the pressure head is negative. That's the distinguishing characteristic of that zone. Below the phreatic surface, it's positive. And so in the unsaturated zone, up where the head is negative, the hydraulic conductivity we use is equal to Kr times Ks. Ks is the saturated hydraulic conductivity. Let me go back here. So this particular problem has a number of different zones represented by the background fill color. In each of those zones, we enter the saturated hydraulic conductivity. But then, if some of that zone ends up being in, some of those materials end up being in the unsaturated zone, we have to change the hydraulic conductivity, and that's what happens here. The hydraulic conductivity is equal to Kr, which is a relative conductivity, times the saturated conductivity. Kr is just a fraction between 0 and 1. So it just reduces the saturated scales or reduces the saturated hydraulic conductivity. And there are two methods for doing that. You may have noticed that earlier in the analysis options dialog box. The version on the right, let's talk about that first. That's the Van Genoegden method. And it has these equations that are defined by these parameters alpha and m. It's kind of an empirical relationship. It defines a nonlinear relationship between the pressure head, ultimately, HP right here, and the relative hydraulic conductivity. So that's the alpha and m are constants, and so the variable here is h sub p, which is negative, and that gives you a relative hydraulic conductivity between 0 and 1. And it's a nonlinear relationship. It's kind of complicated. It's more accurate, but what we generally use is a simplified version called the linear front method. And basically, it might make more sense to flip this on its side, but the horizontal scale here is the pressure head. And 0 means when the pressure head is 0, you're right at the water table. And when the pressure head is positive, over here on the right, this is the saturated zone. So when the pressure head goes negative on the left, this means you're going up into the unsaturated zone. So this this equation describes how KRO varies. How Kr varies. Kr is this multiplier. And so where the pressure head is positive, so everywhere in the saturated zone, Kr is 1, meaning we use the normal saturated hydraulic conductivity. And then there is some minimum pressure head. So this could be, for example, -1 or -2 meters. You can think of it as literally it's like 1 or 2 meters above the water table or above the phreatic surface. And so between HP equals 0, which again is the phreatic surface, and as you go above up to a distance of H min, the Kr term goes from 1 down to some minimum Kr. And once you get above that point, from there on, we just use Kr0, which is this minimum Kr term. Now let me go back to this diagram. So let's look at it. Imagine a vertical slice here in this blue zone here. If we're below the water table, Kr equals 1. If you're above the water table, the phreatic surface, Kr is 1 at this line, and as you go up, it decreases down to a minimum value up to there's some H min value up here. And once you get above that point, it's the minimum value from there up. Okay, And again, that distance could be quite small. I think we default this to like -1. So the the relative conductivity, you know, it ramps down to a minimum value over a distance of over a range of maybe 1 foot or 1 meter as you go above the water table. And so again, it's a really simple method, and it'll when it determines that phreatic surface location, it has to iterate. It's a nonlinear analysis, but it converges very quickly. It's very stable, and it works great. And so you for each material zone, you have to enter an H-min and a KR0, and again, we provide defaults for that. Finally, you have to designate the material properties, and for each material, you give it a K1, a K2, and an alpha. K1 is the hydraulic conductivity in the principal axis of hydraulic conductivity, or that would be parallel to your layers, to your implicit layering inside the material. And K2 would be the minimum hydraulic conductivity perpendicular to the layering. Now this allows you to have an anisotropy that's based on sloping bedding planes, for example, as we talked about earlier in the semester. However, the default value for alpha is 0. And so normally K1 is equal to Kx and K2 is equal to Ky. And that's pretty much how we're going to use it this semester. So anyway, those are the main inputs for seep2d. Once you set that up, you save and run in GMS, and it generates a flow net distribution of heads and flow values. And there are a number of ways to visualize that. We're going to work through, go through, I think, 3 days of examples, looking at all different varieties. This is the culminating method that we'll review this semester. Again, it can be used for just about any profile problem, and so we'll have a good opportunity to explore that. But those are the main features of seep2d.